So in the last part of today's lecture, we're going to look at a design problem. So for Butterworth filter, when it comes to design, it comes to selecting these two parameters. As soon as you fix the order of the filter in and the half power frequency omega c, you're all set. And half power frequency is sometimes called the 3 decibel frequency. Um, and the main idea of design or the main methodology is to go back and look at your frequency response function. Utilize this one in combination with the specifications you were given. Right? The specifications can be given in various forms. Now, the typical form we see is, as we discussed earlier today, to specify the passband frequency and magnitude and the stopband frequency and magnitude. But there are other ways to formulate and provide the design specifications as well. No matter which one you use, you have to go back to the frequency response function. Now, let's just suppose that the design is given in terms of this GP omega p g sub s omega s, and see how we can utilize the frequency response function. Now, one way to do this is, let's say, we evaluate these two, we'll make sure these 2 points are exactly on the curve. So that means what? That means g sub p has to be equal to 1 over 1 plus omega p over omega c squared. That's for 2n. Or in this case, it means omega p over omega c 2n is equal to 1 over gp squared minus 1. Right. Similarly, at the stopband frequency, we can obtain something similar, g sub s squared minus 1. Since these two formulas assumes that these 2 points, gp omega p, gs omega s, are on the frequency response function. Now, taking these two formulas, divide one into the other such that we can eliminate at least one parameter at a time, we have omega p over omega s 2n. And keep in mind that these two frequencies, the passband frequency and stopband frequencies, are two given parameters in your specs. And this will be equal to 1 over, as well as the GP and G sub S. They're all given parameters once you know how your filter should behave. And take the logarithm to such that this 2n can be separated. Or you can take, let's say, 10 as the base. This will be equal to the log 10. And this whole thing, right? 1 over gp squared minus 1, 1 minus g s squared minus 1. And of course, n in this case will be log 10, this whole thing. Divided by 2, log 10, like C. But n is the order of your filter, so n must be an integer. So you usually take the ceiling. You take the integer, the smallest integer greater than or equal to the number in the middle. And that will give you one of the parameter of the filter. Now, as soon as you figure out the order, you plug this back into these two equations. Right, and once you plug in back into this equation, you will end up with 2 omega c's. And when you have these 2 omega c's, You want to figure out, like, you want to know if your design is actually satisfied, meaning you want GP to be less than equal to so that the actual magnitude is greater than the desired level in the passband, and also at the stopband frequency. This must be satisfied. You check omega c to make sure that these two are satisfied. If not, you can adjust the parameter. This will give you a good initial spot. You can change n to be slightly larger and go back to this equation switching. But usually, when you obtain two omega c, plug them into the equation and check. Usually, both of them will satisfy the design. If not, at least one of them should satisfy the design. Now, what I want to know to bring to our attention is here when we do the calculation, GP and G sub S are just the magnitude itself, should be 0.95, 0.05, and so on. They are not in decibels. Okay? We didn't give this GP, G sub S in dBs in this calculation. If they are given in dB, the textbook provides the same procedure, but it uses GP, GS, both evaluated in decibels. Okay? And they use this hat to denote, well, these two magnitudes are evaluated in decibels, and you can refer to the textbook to find out how the calculations should be carried out. Right? So in the homework that you're going to do this week, which is due next Thursday, you have 3 problems in terms of the design of a Butterworth filter. Some of them will require more complex calculations like this. Some of them will just require your understanding of this frequency response function, and just some simple calculations can give you the answer. Okay, so this is the end of this lecture and this week's all sessions. Next week, we'll discuss 2 other filters, the Chebyshev filter and the elliptical filter. I'll discuss the force method assignments, and if we have time, we'll advance to some topics related to discrete time signals.